A heat engine operates on the cycle shown below. It consists of an isothermal expansion AB, an isovolumetric change BC, and an adiabatic compression CA. The volume at B is double the volume at A. At A, pressure, temperature, and volume are given. The work done by the gas during isothermal expansion is 416 joules. The first question: justify why the thermal energy supplied during the expansion is 416 joules. So we should consider the expansion, and it's what? It's AB process. And since it's about energy supplied, we should apply what? The first law of thermodynamics, and actually it's a law of conservation of energy. Energy supplied to the gas goes to increase in its internal energy, delta U, plus work done by the gas. And formulas for the internal energy, it's 3/2 PV, or 3/2 nRT, where N is number of moles, or 3/2 capital N is number of particles, molecules or atoms, and KT. And hence change in internal energy is 3/2 change in PV, it means P2 V2 minus P1 V1, or 3/2 and delta T. And you can see that delta U directly depends on change in temperature, or on temperature only. And since it's isothermal, so since T is constant for expansion, for the expansion process, which is AB, hence delta U is 0, so Q is W, and it's work done by the gas, and it's 416 joules as required. The next question shows that the temperature of the gas at C is 386 Kelvin. So we need temperature at C, and it is given pressure at A. And you may suggest that we can consider BC process, and it's what? It's isovolumetric or isochoric process, and you remember general formula PV over T is constant provided that mass is constant, and if additionally V is constant, it goes to constant, so it becomes P over T is constant, but we don't know pressure at C, this formula to be applied. But we can consider another process, AC, and it's an adiabatic process. And for this process, formula is given in the data booklet, and it says that PV to the power of 5/3 is constant. And by the way, how to distinguish between the isothermal and the adiabatic processes? For isothermal, PV is constant, and hence P is inversely proportional to just V, and for adiabatic it's inversely proportional to V to the power of 5/3, which is greater than 1, so adiabatic is always going much rapidly, it's always much steeper. And also for any process, provided that mass is constant, PV over T is also constant, and we can combine these two formulas to get expression in terms of temperature and volume only. So it's like simultaneous equations if we divide both sides, and we get what? PV to the power of 5/3 divided by PV over T is constant over constant. It's another constant, and you can see that it becomes just V to the power of what? 2/3 T is constant for an adiabatic process. This formula is not given in a data booklet, and it may be a question to show or to get this formula. Or you may consider A and C, and using this formula to find P firstly, and then applying this formula you can relate temperatures and hence find the TC. volumes are given. But we can combine formulas firstly and get formula in terms of volume and temperature firstly, and hence if we consider AC, it becomes V at A to the power of 2/3 temperature at A should be equal to Vc and temperature at C, and we need Tc, and it becomes what? Va over Vc to the power of 2/3 and Ta. But what is Va Vc? It is given that Va over Vc is just a half, because volume here it's two times larger, so it's just a half to the power of 2/3, and temperature at A it's 612 kelvins. And definitely you remember that temperature must be always in kelvins. If it's a change in temperature, it may be in Celsius, but just temperature must be always in kelvins. And hence it becomes, and notice that question is to show that, so you cannot write just that it is equal to 386 kelvins. If question is to show that, you should write the answer to greater number of significant figures, decimal places, and we can write that it is equal to 385.54 kelvins, something like this. And you may write that it's approximately 386 as required. And the next question shows that the thermal energy removed from the gas for the change Bc is approximately 330 joules. And again, it's about energy removed or supplied. It's about what this formula, which is the first law of thermodynamics, or it's just a law of conservation of energy, and Q is change in internal energy of a gas and work done by the gas. In general, if energy is supplied, it's positive, and in general energy can be removed, so it will be negative or something like that. So what is delta U? You can see we can apply these formulas, and since volume is constant and work of the gas, it's what? P delta V, and since V is constant because it's either volumetric or isochoric process, B, we can see the BC, where is it? BC is required. You can see V is constant, so work done by the gas, hence work done by the gas is 0. Hence Q is directly change in internal energy. And internal energy, we can write that it's 3 over 2 PCVC minus PBVB, since we can see the process BC. Oh, sorry, BC. Yes, it's correct. BC final point is C. The starting point is B. Correct. Or it's also 3 over 2 N R T C minus T B. If it would be given number of moles or mass or something like that, we could apply this formula, but to apply this formula, you can see that for A it is given everything: pressure, temperature, volume. For B, T is constant, so it's 612 kelvins. This temperature is found, and actually it is possible it may be possible to find what do we need? We need pressure. In general, it may be possible to find pressures at B and C, but we can solve it in another way. Since mass of the gas or amount or number of moles of the gas is constant, this formula, key formula for an ideal gas PV, is nRT. It will be true for any point, so it's true for PA, VA, TA, PB, VB, TB, or PC, CVC, and TC. And since everything is given for point A, we can write that it's PA, VA, and is constant TA. And we can just solve for nR and substitute into this, and we know TC and TB, and we don't need to find pressures. In general, definitely it's possible to find pressures and then use this formula, but it will be more useful to use this. So, and hence Q, or we can continue, it becomes 3 over 2, and I is PA, VA over TA, and this TC minus TB, and it becomes 3 over 2 pressure at A. Pressure at A is 4 times 10 to the power of 6, and volume at A it's 1.5 times 10 to the power of negative 4. And what about temperatures? Temperature at A it's 612, and TC it's found, it's 386 minus TB, since it's isothermal, temperature is constant, so temperature at B is also 612 kelvins, and you can see that it becomes negative, and that's why internal energy decreases, hence energy is removed from the gas. And if you calculate it, you get that it is equal to negative 332 joules. And again, the question is to show that approximately, so we show to larger number of, to greater number of significant figures. If it would be a question just to calculate, it's reasonable to calculate two significant figures, because everything is actually no, 3 significant figures, because you can see that everything is given to 3 significant figures. And actually, if question would be just calculate, the answer would be also to correct to 3 significant figures like this. And the next question, determine the efficiency of the heat engine. Efficiency, there are 2 formulas in terms of temperature given in a data booklet, and in terms of energies, it's not given in a data booklet, but it's energy in minus energy out and divided by energy in. And here, since energy in is only during AB, and since it is shown that it's directly 416, minus energy out, it's the only process, it's BC, because CA is adiabatic, it's Q is equal to 0, no change, no heat exchange with surroundings, minus 332 and divided by 416, and it becomes 0.20 or 20%. And the next question, B. State and explain at which point in the cycle the entropy of the gas is the largest. What is entropy? Entropy is a measure of disorder of a system. Or we can use the next formula that change in entropy is what? Delta Q, or just Q, or let it be delta Q divided by T. Q, delta Q, it doesn't matter. And we can solve it in the next way. So since AC is, oh, let's draw it again. A, B, C. Since AC is an adiabatic process, Q or delta Q is equal to 0, hence change in entropy is equal to 0. It means entropy at A is equal to entropy at C. Then, if we consider AB, for AB, temperature is constant because it's an isothermal process, and energy is supplied, so delta Q is positive, so entropy increases. So entropy at B will be larger than entropy at A. But so we can conclude that entropy at C is equal to entropy at A, but entropy at B is greater than entropy at A, and hence greater than entropy at C. And that's why at B entropy is maximum. And that's all for this question.